So good morning, everyone. Okay. So welcome to this Smart Energy Management Part 1 presentation. My name is Alessandro Piccinini, and I am one of a researcher of the National University of Ireland and R2M Solution. And just to clarify, each of you has 15 minutes to present. And so I know that the time is short. And so the first paper is distribution grid energy flexibility, the Ebalance-Plus technology development for the University of Calabria demo site. So it's Anna Pinnarelli. So let's start.
Okay, good morning, everyone. I'm Anna Pinnarelli from the University of Calabria, from the research group of electric power system. So I share my screen. Do you see my presentation?
Yes.
Okay, perfect. So today I will present my contribution with title Distribution Grid Energy Flexibility, the Ebalance-Plus technologies developed for the University of Calabria demo site. The goal of this presentation is to describe the aim of this demo site to test several technological solutions to increase and to exploit network flexibility and the reliability of grid. This is a result of H2020 project Ebalance-Plus. So we can start with the presentation. It is well known that the increase of renewable generation and distributed energy resources, and consequently the decrease of dispatchable plants, determine the distribution network have to face new operational challenges. So new regulation and balancing service have to be deployed. In particular, several scenarios have been outlined in terms of energy flexibility, and so in particular of local market flexibility, creating new opportunities for the distributed system operator. In particular, in this context, the Ebalance-Plus has the aim to increase network flexibility and resilience by creating and integrating smart energy technologies into an energy balancing platform. In particular, this H2020 project will develop technological solution, in particular will propose a local energy market model that will be tested in 4 pilot sites. One of these pilot sites is the University of Calabria campus, UNC demo site. We have what is the objective of this UNC demo site? We have different ways to provide energy flexibility. The principle is the use of energy storage system for local services such as peak sharing, or for system services such as frequency, voltage regulation, and to face the problem of grid congestion. Other solution is the use of demand response program, for example, for the service of load shifting. The UNC demo site has been implemented to be able to implement and observe what has been described and defined theoretical in terms of flexibility, resources, and services. So we can describe briefly the University of Calabria campus. We have several office and residential buildings, laboratories, classrooms, library, and so on. For each building, we have a PV plant installed on the rooftop with a total power peak of about 1 megawatt. These buildings are supplied by a primary and medium voltage substation, and with a ring distribution in medium voltage, and we have also 28 medium and low voltage secondary substation. So we can consider this campus such as an aggregation of several consumers, prosumers, and producers. So it is a significant test facility to test and to evaluate the benefit of innovation of new technological solution. The objectives of NC demo site in a balance project is to increase the energy flexibility of some buildings, not all. In particular, we have considered 5 buildings, 4 office buildings in terms of consumption and generation. So consider the use of IoT devices and smart appliances to enable demand response program, and also for PV power modulation. The other objective is to increase the grid reliability, supporting the activity of distribution system operator. The other objective is to simulate and test the benefits of demand response program to manage, to unlock the energy flexibility resources. The main object in terms of devices that will be installed in demo site, ONC demo site, to improve the control, the automation, and the communication of each infrastructure involved in a demo site. So the primary substation, the secondary substation, the office building, the residential buildings, and integrate this infrastructure in a energy management platform of Ebalance-Plus. In particular, the demo site configuration consists of medium voltage primary substation named Mega Centrale, that is illustrated in this picture. For office building named Cubo, we have in particular this office building with the medium and low voltage secondary substation that supply this office building. 5 apartments, student apartments of a residential district that is Monaci. It is this in this picture, and finally it is involved in demo site also an experimental microgrid installed in a residential district named Chiodo 2. This experimental microgrid consists of 3 nanogrid with a direct current distribution, operating as a single CDC microgrid because it is connected to the MV medium voltage ring distribution of Unical Campus. This microgrid integrates 2 PV planes, one conventional PV plane and one custom PV plane, because the inverter is not a conventional inverter but a nanogrid developed in our laboratory. We have also one Stirling engine microcogenerator, micro CHP, a lithium battery storage system. We have also several electric loads and particular controllable loads, and in the last, one heat pump and a thermal storage. In Mega Centrale, we have installed a smart meter, and we will install a management unit and several sensors. The scope is to evaluate the voltage quality at the point of delivery of the whole campus, Unical Campus, and also to optimize the reactive power, and in particular to monitor the status of transformer of secondary and primary substation. In office building, we have installed the smart meter to monitor the consumption and the production data, in particular the photovoltaic production. We will install a management unit to control the distributed energy resources named DERMU, and we will install also a smart storage system. The scope is to implement demand response program, so to obtain the optimal control of DER, such as a virtual power plant, to reduce energy price and CO2 emission. In this slide, we have some picture of the component that we have installed or will install in demo site: smart meters, the smart grid management unit, that is that will be a medium voltage management unit for the substation, and DERMU for the office building, and a picture of a smart storage system, that a commercial smart storage system. In Monaci, we have installed the smart meter to monitor the PV plant for the whole residential building, but also we have installed a single smart meter for each apartment. We will install a DERMU for each apartment, such as IoT devices and smart appliance, so to realize a interaction with the student of the lived in the apartment, to implement the demand response program, and also in this case for the optimal control of DER, and to reduce energy price and CO2 emissions, such as like the office buildings. We have illustrated some of these smart appliance and IoT devices. In particular, we have we are implementing also a smart app to control online the smart appliance, considering the results of the area program, and so the input control sent by the Balance Energy platform. In Chiodo 2, we have this is the experimental. In this picture, we have reported the picture of experimental macrogrid. We have the 3 nanogrids, the ceiling micro CHP, the PV plant with the inverter conventional, the lithium storage, and the display for the energy platform. In particular, in this case, we can realize both reactive and active power modulation based on the output of optimization algorithms in terms of flexibility management, PV and load prediction, CO2 and energy price optimization, and so on. These control signals will be sent by the Ebalance-Plus energy platform. So I have finished with my my presentation. The final point is that the future steps is to connect these all these devices, so this component with the Balance-Plus platform, so to test the management algorithms. Thank you very much for the attention.
Thanks a lot for the very interesting presentation. So is there any question? No? Okay, I would like to know when the project is going to finish. When do you have in plan to
yes, in February of 2023.
Okay, perfect. For me, yeah. It's fine. Thanks, thanks a million.
Thanks you.
Okay. So let's go with the next. So the next presenter is me. So Alessandro Piccinini. I will share my screen. Okay. So. Okay. So, okay. Hello, everyone. My name is Alessandro Piccinini again, and I am a researcher of the National University of Ireland and the R2M solution. Today, I'm going to present you the main outcome of my research, but also one of the digital twin tool of the Sphere platform, so the ModSCO web application. So, okay. So very quickly regarding the Sphere project. So Sphere is a 4-year Horizon 2020 project that aims to provide a BIM-based digital twin solution to optimize the building life cycle, reduce cost, and improve energy efficiency in a residential building. So we are 18 partners from 10 different countries, and the project is going to end next year. So before introducing you the ModSCO web application, I would like to give you a very quick background. So as you know, the European Union is developing policies regarding the renovation of buildings, such as the near zero energy building or the decarbonization of building stock by 2050. And one of the potential measures is the energy performance contracting. But there are still some barriers for the application of the energy performance contracting, such as the process complexity, the common lack of information about the building, and the uncertainty about the post-renovation energy performances. For this reason, some years ago, we decided to develop the ModSCO web application. So the ModSCO web application is an easy-to-set-up building simulation tool that is able to estimate the energy savings due to energy conservation measures by utilizing the IPMVP framework, that is one of the measurement and verification framework. So just to let you know, the ModSCO define a whole building energy model just utilizing just 28 parameters, and it is, let's say, filled with data simply available in building retrofit. So the ModSCO web application is useful both in the design phase for a quick estimation of the energy consumption of the building, so both electricity and fossil fuel, but it's especially useful in the operational phase for a continuous evaluation of the energy savings in buildings. So I'm gonna talk very quickly about the core platform. So the core of the ModSCO web application is a Python script that is developed with PyFMI and the dependencies. And this Python script is stored in a web server and a talk with the web application with the API. So this Python script run a functional mockup unit, and this functional mockup unit contains the real core of the application, that is a reducer order gray box model that was developed by using the Modelica programming language in the Daimon environment. And this reducer order gray box model simplified the physical description of the building by utilizing the thermal network analogies, by means resistances and capacitances. And so this is the RC schema of the Modelica model. So in this graph, you can see the a graph regarding the utilization of the web application represented with the business process model notation 2.0. That is a method, a workflow that facilitates the understanding of the graphical. And the utilization of the application is divided by 3 phases. The first phase is the parameters calculation. The second phase is the simulation and calibration. And finally, the third phase is the parameters estimation. So in order to explain you the full workflow, we applied the ModSCO web application to an university building located in the heart of the National University of Ireland in Galway. So this building will be retrofitted next year with several energy conservation measures, PV panels, a new glazing system, insulation in the envelope. And so the scope of the test was to estimate the energy savings by creating the baseline period energy consumption of the building. So basically, the baseline period energy consumption is the consumption of the building as if the energy conservation measures were not installed. So basically, after the retrofit, we will run our model and we will compare our baseline with the real consumption of the building to calculate, to estimate the energy savings. So this is like the IPMVP method. So in order to create this baseline period energy consumption, we collected the energy bills and the building data from the building. And so the first phase is the parameter summation, as I said. So this phase is done by utilizing 3 Microsoft Excel based tool. This Microsoft Excel based tool are Rampart, the internal gain calculator, and the schedule creator. These tools is possible to download the tool directly in the website, so in the GUI of the application. And this tool produces 2 TXT files. So these TXT files have to be uploaded in the web application together with a list of parameters. As I said, these parameters are easily available in building retrofit. So for instance, parameters is the building latitude, the building volume, the set point temperature of the room for cooling and heating. And as you can see, the parameters are divided by a first part that are the building parameters that are estimated from the building data. And the second part are the calibration parameters that are used in the calibration process. So all these parameters are inserted in the web application, and this process took 2 hours, so to calculate all the parameters. That is like to develop the geometrical model in a wall building energy model. So once we inserted all the parameters, we can start the second phase, that is the parameter ModSCO simulation and calibration. So we have just to click run simulation, and what will happen is that this list of parameters will be sent to the Python script through the API, and the Python script will run the model, and this will produce the baseline period energy consumption not calibrated. So like all the energy models, so the wall building energy model, also the ModSCO web application has to be calibrated, so the model. But the calibration is quite simple and consists in an iterative procedure in which the parameters considered uncertain during the calculation of the parameters are changed. So in this case, we choose just 4 parameters. That was the calibration one. And so for each set of parameters, we run a simulation, and the result of the simulation, so the baseline period energy consumption, is compared with the real consumption of the building based on the 4 statistical value listed in the slide, so NB, CB, RMSE, R square, and the monthly deviation. So if the result of the comparison, so this value, are under the IPMVP statistical limits, we consider the model calibrated. So these are the final values of the calibration in the table. And these are the result of the calibration. As you can see, the ModSCO model was under the IPMVP statistical limits, and we had good result for both electricity and natural gas, because the building has 2 sources of energy. And this process took just 4 hours. So then the last phase is the estimation of the savings. This phase will be done once all the energy conservation measure will be installed in the building. So in 2022, in theory, in January. And what we will do is that we will update the parameters according to the reporting period, so after the installation of the energy conservation measures. So an example is to change the weather file from the one used in the calibration to the one used during the reporting period. Another example could be the occupancy of the people if it is changed during the reporting period. And once we updated all these parameters, we can run the simulation, and the model will generate the adjusted baseline period energy consumption. So that is basically, as I said, is the consumption of the building as if the energy conservation measure were not installed. So this adjusted baseline period energy consumption will be compared with the actual energy consumption of the building, so the real consumption of the building after the installation of the energy conservation measure, so the green line, and we will calculate the energy savings. So in order to simplify this phase, we have a tool that is able to calculate the savings and also the calibration precision according to the precision of this energy savings according to the calibration values. Finally, in order to let's say estimate the benefits of the model, we compared our procedure with a wall building energy model developed with ISV. So basically, we developed with ISV. We created with the ISV the baseline period energy consumption. And as you can see, the ISV had very good result as well, both for electricity and natural gas. But while with the ModSCO web application, we spent just 6 hours for the development and for the calibration, with the ISV model, we spent 40 hours. So this was due to more time to generate the geometrical model. We spent time for a new survey needed to feed the parameters of this detailed model. We spent a bit more time for the calibration since there were more parameters to control. The conclusion. So the ModSCO web application provides a quick and accurate method for reliable quantification of energy savings achieved through energy conservation measures, an easy-to-use tool for quick evaluation of building energy consumption, and a novel methodology to support measurement and verification in case of uncertain in building retrofit, because this is the main point, because basically if we have the full data, also calibrate a whole building energy model is simple, but usually in retrofit building we have a lot of uncertain, and so the ModSCO web application could be very useful to estimate the energy savings. So the web application will be fully available at the end of this year because it is still under testing. And thanks for the attention. Any question? Yeah, okay.
Modeling, but how are you working? How are you making benchmarking between your estimates and what are really going to be the savings?
Sorry, so can you talk?
So you are making an estimate what is going to be the savings, right? But
Yeah.
how are you checking your
Okay, yeah. So that's a good question.
The modeling of the losses using the thermal modeling with the capacitors and the distances is very effective, at least in semiconductor losses. But there you really know what are the geometry of the semiconductor material, model materials very well. And so the estimates are really precise, maybe up to 5% error, or less than that. But in a building, you know the geometry of the building roughly.
Yeah.
You know the materials again roughly. What is going to be the end result? How precise your estimate?
Yeah, basically, this is a good question. Basically, as I said, we introduced in the model some parameters called calibration parameters that are used in the calibration process to cover all this uncertainty. Okay, basically, this model is checked just for, let's say, monthly consumption. We tested the model also for hourly consumption with good results, but we prefer to keep the model for monthly estimation. Okay, and let's say that in this case, this is the first test of the web application. But we tested the model also, the Modelica model with several buildings, and we do also several validation. So not only like here estimate the savings and that's it, but we validated with the year after the results. Okay, and so you can see like my paper with excellent results. So basically, the model is used for the creation of the baseline period energy consumption. That is, like, as I said, the consumption of the building as if the energy conservation measures were not installed, but could be used also for the application of envelope scenarios. So basically, let's say that our validation was to check the consumption of the year after, and since we got a good result with several buildings, we decided to consider the model a good choice for the creation of the IPMVP baseline period energy. So that's all. So my time is ended. So I need to introduce the next speaker. That is Aggeliki Aggeli. Is these people here with the paper promoting co-creation as intermediation for household demand response solution? No? Okay. So, okay, let's go ahead with the, let me see if it is she is online. Okay, probably not. So let's go ahead with the next speaker. So the next is data security in smart buildings of Bushra Cannan. Okay, you can come here. Okay. My presentation should be one of these. This one.
Yes, that's the one.
Okay.
Well, hello everyone. My name is Bushra Cannan, a PhD candidate, currently enrolled in a co-tutel program from the University of Haute in France and the University of Freiburg in Germany. And today I'll be presenting to you our work on the cyber-physical security in smart grids. We're a part of the interREG project, the RESTMO, which stands for Modeling Regional Concepts for Renewable Energy Production and Storage in the 3 national metropolitan region of the Upper Rhine. We have partners from the academia. From France, we have the University of Strasbourg, the University of Alsace. From Germany, we have the University of Freiburg, the Kpi Institute of Technology, and the University of Bâle. In addition to several partners from the industry. The project will be presented later by Professor Barbara Koch this afternoon. We're holding the work package number 7, which is about data security in smart grids, especially in the region, in the Upper Rhine region. And in this work package, we are responsible on reporting the latest European legislation on the data security. Also conducting interviews with the responsibles of the operation systems. Then we move to the motivation or the context of the work. In fact, the problem of securing energy system has evolved from finding new resources into dealing with the problems arising from these resources, which is the renewable resources in particular, which is the quality of the energy systems, which took another turn when we addresses these problems by intensified usage of digitalized systems that heavily depends on information, on communication and information technology. So, what is cyber-physical security? The interaction between the power system, the communication system, and the information technology is what's called cyber-physical system, and which is concerned by the cyber-physical security. The reason why academia recently chooses to add the term physical to the equation is to shed the light over the emerging threats imposed by connecting these 3 fundamentally different infrastructure together, which practically may lead to threats emerging or caused by the interaction of these fundamentally different domains and do not particularly belong to any of them. Securing the CPS is related to the detection and mitigation of cyber attacks that bypasses the barriers of the protection met by the specialists in the information domain. The attacker in these cases would not only have the control over the automation system, the computers, but also will have the a knowledge about the physical system in order to cause damage to the physical equipments. The National Institute of Standards and Technology, the NIST, has defined the security criteria in these categories: the confidentiality, the integrity, the availability. Some references also add accountability. Smart grid security or network security is also built upon these previous criteria, but with a different order, as we can see in the picture. Despite the fact that cyber intrusions on cyber physical system can be found under different terms, but upon the previous discussion, we can categorize these attacks into two main categories, which is upon the security criteria that they are jeopardizing, such as for the attacks that target the availability, it's a denial of a service, the DOS, and the attacks that targets the integrity of the information between the components of the system, it's called the FDI, or false data injection. No matter the approach used to induce an attack, the objective will be in the range of causing a minor degradation of the system and could reach up to destroying parts of the system or causing a physical damage of the equipment. In the cadre of the InterREC project, we are committed to addressing problem on a larger scale on the the three national metropolitan region. But we found that the performance of such security assessment is highly complex in such larger interoperability systems. That's also because to the difficulty to trace not only the proposed solution, but even to trace the attack impacts. In addition to the fact that solution cannot be only technical, it must be a multidisciplinary solution that also cope with the energy market and the legislation in the three countries. In addition to the social concept, of course, also. So we decided to work on a smaller scale, which is the scale of microgrids, for different reasons, because already microgrids are now considered as a building blocks of the smart grid environment. And it also supports the tendency towards decentralization of the energy system. And it plays a huge role in risk management in terms of regional resiliency and preventing cascading failures in terms of when we were run into events such as extreme weather conditions or even cyber attacks. It's also considered as an effective solution in terms of managing the current the current grid problems regarding control mechanisms and stability problems, and the integration also of the small-scale renewables. Now, microgrids are also considered as a cyber-physical systems, since that it has both or three basic, fundamentally different infrastructure. But it should be noted that the safe operation of smart microgrids or the energy the power management strategy in microgrids is more critical because we have these minor sources and it's very dynamic. So whenever we don't have, for example, the inertia that it's already existed in the big scale grids. That's why microgrids are a fairly tempting target for the attackers, depending, of course, on the attacker incentives, which may include data theft, or energy theft, or data leaking, or even jeopardizing physical infrastructure and equipment. Of course, the success yardstick is highly correlated with the competences of the attacker and the presence of security gaps that might be included. For further information about the microgrid cybersecurity, we invite you to check our publication on this subject found in Applied Science Journal. Now, for our technical contribution, what we are doing here is to try to develop an IDS, which is an industrial detection system, which stands for a tool or a mechanism that used to detect the attacks against the attacks in a system or a network by analyzing the activity in this in the system. Of course, selecting the right type of the artificially intelligent tool to use is very essential. In this experiment, we have selected the recurrent neural networks, which is very, it has a good reputation with dealing with sequential signals. We have selected also particularly the type that's called auto-regression exogenous neural network, the NUIG. And what mainly our trained network is meant to do is to understand the relationship between the different components of a system, of a microgrid. And it could then tell us when there's a component that does not act incoherent with the other components, which is very effective in the FDI attacks, especially there's also the replay type of attack, in which the attacker records the behavior of one component, save it, and then re-injects the same type, the same signals. Moving on to the data, the selected data for the training for the network was obtained from a fully simulated microgrid we found on an open source on MathWorks. It contains all the essential elements of the microgrid, and it was already implemented on in a way that it can be easily transmitted to the real-time simulation, because the next step will be to move a part of this simulation into a hardware in the loop simulation performed by our partners from OpenRT Technologies. And for further details about this experiment or this implementation of the method, we highly recommend that you check the work published on the IZ conference under the title of Detecting Cybersecurity in AC Microgrids Using Artificial Neural Network. Thank you for listening.
Is there any question?
Yes.
This may be a simple question, but what sort of information are the consumers supposed to exchange with each other? I mean, if we consider that the control of the consumers is probably going to be decentralized, so they are going to work essentially autonomously, what kind of information they are supposed to exchange, and why is that any different from the exchange of information currently we are doing when we are paying something with a credit card or anything else? I mean, why is the cybersecurity in the microgrids so popular at the moment? I mean, I'm not really familiar with this, but
yeah, well, it depends on the attacker incentives, because now, as I said, it could be only for energy theft. There are people who would like to manipulate, for example, their production or their consumption of the energy to gain on the economic level, for example. And in other cases, which is the case that we're mostly concerned in, is the case where the attacker wants to do a physical damage. For example, if I send a reverse information to the sensors that are meant to control the system or to regulate the energy between the different distributed resources and everything. If I send or if I communicate a false information, that could lead to a physical damage of one of these components, and that's what we are concerned about in this subject or in this work.
That's also bringing another problem. I guess it's the 6th slide. Right?
Okay.
There is, I guess, the action in which the prosumer is supposed to be to destroy. I'm not sure, perhaps I didn't understand it, but stop the attack system. So again, the attack, perhaps, I mean, I'm not really familiar with this, but perhaps the attacker isn't able to really do anything dangerous, but as a mitigating action, we would turn off that prosumer. And that actually is introducing the instability. So perhaps so I'm just trying to say that the actions, the actions that through which we are supposed to keep the microgrid operational are perhaps going to
exactly.
involve some.
I believe you mean in the terms of cascading failure, when the failure moves out from the microgrid scale and goes on to the distribution network. Yeah.
If we have just 5 nodes, if we turn off one node because we are thinking of something going to happen, the whole microgrid could fail, even though the attack perhaps isn't very serious.
Exactly. Well, until this moment, since that microgrids are not as essential part of the grid nowadays, we do not have that as a very obvious problem. But I guess if these kind of system, or if the decentralized systems take over what we have here, maybe then we'll be facing some more serious problems when it comes to this sense. I mean, okay.
To pass to next So the next speaker is Todorović, or Ivana Isakov, with the paper Advances in Distributed Generation Sources, Digital Twin Design.
Thank you. Good morning. My name is Ivana Isakov, and I'm here in front of the Typhoon Hill company, and I will talk about the advances in distributed generation sources digital twins design. In Creators project that we are involved in, and that aims at creating local energy communities, we actually use digital twinning in order to try to minimize hazards of community energy systems usage. Also, we are trying to see how can we maximize the profits and minimize the financial losses, and see to how can we facilitate the development of new features, explore new business models, and also how to enable grassroots incentives. Generally speaking, we want to see what will happen with community energy systems as soon as possible, and not just to wait some time to pass to see what will be the results in the field. A digital twin is actually a digital replica of a multi-domain system that may contain several subsystems, such as electrical, mechanical, chemical, thermal, telecommunication subsystem, and so on. And depending on the complexity of the model, it can be executed slower, faster, or in real time. Of course, as the platforms that are used for digital twinning improve with the time, also does the complexity of the model and size of the model that can be tested. When it comes to the traditional approach to the digital twinning, we have three topologies that are most widely used. These are model in the loop, software in the loop, and processor in the loop. All these three topologies are dedicated for offline simulations and are based on the PC personal computer simulators. So they are pretty much that is a safe environment, but unfortunately, since the resources are restricted, the simulations are slow. For the model in the loop, both power stage and the control scheme are implemented in a software tool in the computer, and if we are using the software in the loop topology, then a control is actually embedded using some embedded programming language, and that help us to see and check the syntax of the program and see how the code is organized. On the other hand, if we are using the processor in the loop topology, we have the control code that is downloaded to a real controller, but that controller does not operate in real time, since it has to be synchronized with the PC in order to exchange the informations. So here we have just an insight to the controller's resources utilization. So that would be a benefit of this approach. If we want real-time simulations, we have to use either controller hardware in the loop topology or power hardware in the loop topology. In both cases, we need to have a dedicated hardware, which is usually called real-time simulators or emulators, that are used instead of the PC for the power stage modeling. If we are using controller hardware in the loop, then in that case, the power stage is emulated using the emulators, and the control code is downloaded to a real controller, and the controller communicates with the emulator unit through an interface board, and that interface board is in this case simple. The emulators are sending the responses of the emulated system to the controller, and then the controller takes actions and returns back through the interface board control signals for the system. Here, the test automation is easy to be enabled, so this actually significantly improves the process of the testing. But in the power hardware in the loop topology, a part of the model can be emulated using the emulators, while the other part can be implemented using the real hardware. For example, some kind of prototype or something similar. And then, again, we have the controllers with the control code, and this topology is good if we want to test a real piece of hardware. But since we have a real hardware, this is not so safe environment anymore, since some kind of a mistake during the modeling process or testing process can cause a hazard on the real equipment. Also, here, power hardware and power stage emulated in the emulator have to be connected using the interface board that is not so simple anymore, since signals from the emulators have to be converted to real voltages and real currents. And also, due to the fact that we have the real hardware and we have to be careful, the automation testing is not so flexible as it is in the controller hardware in the loop topology. If we want to emulate larger and more complicated models, we should use co-simulation, which means that we should use a combination of, for example, C-hills, control hardware in the loop, and P-hills, power hardware in the loop topologies. And in that case, since we are using the emulators, which have more resources, we can achieve real-time simulation. But we should use more than one emulator unit in order to emulate such large systems. We have different variants here. We can use a combination of different C-hills. So in that case, we have more than one emulator unit, and we have the controllers. And this is the most widely currently used type of the co-simulation. Also, we can use only hardware-in-the-loop or emulator units, which is a step further. So if the controller side is not so important, the hardware, the controller side, then we can just emulate using the emulators, both power stage and control, if we, of course, have enough resources. And in that case, depending on the model complexity, we can even achieve faster than real-time execution of the model, which significantly improves the testing procedures. Another variant is to use C-hills and P-hills, which are geographically dispersed. In that case, they're communicating using the internet. This is a good approach if someone does not want to share details about the model and maybe all parameters of the model, but is willing to give the model at the disposal to someone else who can use it and test it. So someone can use the model without knowing how the model is implemented, what are all the parameters, but can use those resources through the internet. So in that case, the problem of data security is solved. But there is a problem of the data latency since we are using the internet communication network. And also, this may be difficult to manage if there are a lot of geographically dispersed subsystems. So they have to work in the coordination to achieve better and reliable simulation results. So as I said, today, most widely used co-simulation techniques are using the C-hills, a combination of C-hills or only hills. And the future would be to use the C-hills or hills behind the cloud. So in that case, someone may access the models through the cloud using the application programming interface. So you can create the models, parameterize the models easily using API calls. And also the benefit of this approach is that the introduction of third-party services can be also met, since third-party services now can access the models and may use them for some kind of analysis, financial analysis, and so on. Also, offline simulators can be used behind the cloud. All these combination C-hills and hills can be used in real time online, but those can be also used offline. In that case, we can also achieve faster than real-time execution. And depending on the, there is, of course, a trade-off between the system complexity, system resolution, and the speed of the execution. So the good thing is that the models are back and forward compatible in the sense that the resolution of the model execution can be changed online. So the future is definitely using the cloud services to emulate. Okay, so I'm just going to give you a brief example. Sorry. So here the facility with a battery system, a PV system, and two controllable variable loads was modeled using two approaches. The first approach is more detailed. So here the power stage was actually modeled. And in the second approach, the signal processing components were used to mimic the behavior, dynamic behavior of the real power stage. And three of these facilities were included in the final model. So the final model has 3 PV systems, 3 battery systems, and 6 passive loads. That is now a moderately complex system. And it can be, of course, as I already said, executed using the emulators, using the local PCs, or using the cloud. So different speed of execution can be then achieved. If the model is executed on simulators, for the approach 1, we managed to run it in the real time. And for the approach 2, it was even faster than real time. And for the time step of 20 microseconds, it was 100 faster than the real time, which is really remarkable. So here we have two different configurations. The same emulator unit was used, but with two different firmwares. So as we can see, 100 times faster than the real time really gives us the possibility, for example, to simulate 1 year for a couple of days for some models. If the model is executed on the local PCs, then for the first approach, we are again near real time, slightly faster or slightly slower. But in the second approach, we again managed to be faster than real time, slightly slightly less fast than in the case that the emulators are used, but fast enough. So again, we can see that the configuration of the PC slightly affects the execution speed. When it comes to the execution through the cloud, this is now under the testing. Results are coming. We expect that if the emulators are used behind the cloud, that we are going to have, again, real-time execution speed. But if servers are used, then we expect even faster than real-time execution, since the servers have much more resources than PC personal computers. So you can check up and follow up the Creators project to see what will be the results of this testing. And just to make a brief conclusion, digital twinning is definitely a sophisticated and very powerful tool in the modeling of large and complex systems. Different approaches are possible. We saw some approaches, and we are now capable to emulate large systems even faster than real time or in real time. And also the future is definitely in the integration with the cloud services and the introduction of third-party services that may use the models for different kind of analysis. Thank you very much. Yes.
Is there any question? So I would like to know, it was very, very interesting. Your research, do you guys have case inside the project?
Yes, we are making digital twins of pilot sites that we have in project to see what will be the benefits in general of creating local energy communities from on these pilot sites. Okay.
No question. Thanks.
Okay. Thank you very much.
Okay, so the next speaker is Chris Ogwumike. That sorry for the screen. That should be online, but is okay. Here you are. So the next speaker is Chris Ogwumike with Kpi Evaluation Framework and Tool Performance, a case study of inteGRIDy project. So can you hear me, Chris?
Yes, I can hear you. I'm trying to share my presentation.
Okay.
So what I can see is just my, my video, but I can't see the presentation. How do I go about that?
Okay, let's see if I have your presentation on my computer. No, you should click on the little screen below your the presenters. I don't know if you can see. I will share my screen.
Okay.
Sorry. Hey, I'm sorry. So, the previous presenter.
So
Yeah.
where do I need to click to be able to share my presentation?
Let's do like that. I will let him present, and then I will ask questions, the previous questions. Sorry for that. So I will share my screen, and I will let you see where you should click.
All right, thank you.
So you should click on this icon here on your laptop.
Okay.
Okay. Do
Right.
you have it?
Yes, I do.
Okay, perfect. I will stop sharing mine.
Okay.
Okay, perfect. I can see your presentation.
Okay, yeah, that's fine. Thank you very much. My name is Dr. Chris Ogwumike. I work as a research associate in the School of Computing, Engineering and Digital Technologies, Teesside University. And I'm focusing on the inteGRIDy projects. And today I'm going to be presenting the paper titled Kpi Evaluation Framework and Tools Performance, a case study of the inteGRIDy project. Just as an overview of what I have to present today, I will give some background and motivation of the inteGRIDy project. Then I'm going to focus on the Eye of White pilot use cases, the Kpi evaluation results and analysis. Right, inteGRIDy project is quite a very huge Horizon 2020 projects, European projects that comprises of 28 partners from both industry and the academia. 33 use cases focusing on 4 main inteGRIDy thematic pillars, which includes demand response, battery energy storage, smartening the distribution grid, and electric vehicles. And this is across 4 domains: technical, economic, environmental, and social domains. And that's being implemented within 10 pilot demonstration sites. And this inteGRIDy project is aimed at integrating cutting-edge technologies, solutions, and mechanisms in a scalable cross-functional platform of replicable solutions, which will advance the optimal and dynamic operation of distributed generations, fostering grid stability and coordinating distributed energy resources, virtual power plants, and collaborative storage schemes. So having said this, let's focus on one of the pilot sites, which is the Eye of White pilot site. And within this pilot site, we have 2 thematic pillars. One is under demand response. And for this thematic pillar, they use virtual power plant technology for advanced building energy management control. And for this thematic pillar, the use case that is applicable here is called building optimization to maximize energy efficiency and demand flexibility. The second thematic pillar that is applicable to this use case is energy storage technologies using heat pump control hub. And the use case for this is called M7 energy storage systems. So for both use cases, we have selected some key performance indicators that show significance for evaluation. And we are doing this by comparing the baseline and the smart solution scenario that have been implemented in the course of the inteGRIDy projects. So through the evaluation phases, we identified 4 key phases. The first is defining and analyzing evaluation parameters. So this is where we selected the KPIs that show significance to the objective of the use cases. And the second is to select the appropriate methodology for evaluation. The third is the mechanism for data connection as needed for the evaluation process. So we focus on technical quantitative data connection, which was mainly based on M-series data. as well as structured interviews, questionnaires that are designed to collect quantitative data for baseline and smart solution scenario. The baseline scenario is the scenario before the start of the integrity project, and the smart solution scenario is what the scenario and the implementation during the course of the integrity projects. And the fourth phase is the evaluation process and analysis of the connected data. So based on this, we'll look at the different evaluation methodology that we followed. First, we started with the validation of the KPIs, the KPIs that has been selected for the different use cases. And we started having discussion to check whether the KPIs are still valid for the evaluation of the use cases. And of course, the KPIs that we evaluated naturally evolved after closer interaction, closer meetings, discussions with the pilot site partners. And after that, we developed a KPI calculation template showing the description of the KPIs, the formula to calculate the different KPIs. Having done this in stage 4, we performed a test KPI calculation using some arbitrary baseline and smart solution data. After which we now proceeded with the data connection for baseline and smart solution. And within the data that we connected, we ensured that the data are pre-processed and fit for purpose. After which we now use the data to perform KPI evaluations, obtain the results and the analysis. So just looking at the preliminary result that we obtained for the first use case, which is the building optimization use case. And this use case deals with the building optimization through demand response event schedules. And this is such that the participants in the demand response events we are requested to either increase, decrease, or hold their energy consumption with the aim of maximizing the grid efficiency. So as we can see in figure 1 and 2, we present the result for this analysis. And of course, it's important to mention that based on the applied contractual framework limitation in the Eye of White pilot site, each demand response event request results in a 10% change, which could be a 10% increase in energy consumption, as we can see in figure 1, or 10% decrease in energy consumption, as we can see in figure 2. And it's worth noting that although not much difference is seen in these figures, the aim of achieving a grid stability has been achieved in this use case. And of course, we also presented the KPI evaluation results for the technical, economic, and environmental domains in table 1 to 3 respectively, showing the baseline energy consumption as well as the demand flexibility request, which in this case is 10% increase and 10% decrease in energy consumption. And for the technical KPI in table 1 here, an additional energy consumption of 349 kilowatt hour was obtained for energy consumption reduction in T.04, whereas a reduction of 558 kilowatts of energy was obtained with 10% decrease. We also presented the results for the economic as well as the environmental domain. And the second use case that we evaluated is the M7 energy storage use case. This use case involves the use of heat pump to store energy during the period of no electricity cost, which could then be utilized at the later stage. And looking at the results for the analysis across the 4 seasons of the year, the winter, the summer, the spring, and autumn, in figures 3 to 6, respectively. we can visibly see from these figures the differences between the baseline energy consumption in blue and the smart solution implementation in orange. And of course, these differences are more visible in the winter, spring, and autumn. However, in the summer, as we can see here, the heat demand is low, hence that has been reflected in the low energy consumption for the smart solution in figure 4. And we've moved forward to perform the overall, to get the overall energy consumption using 1 year of data for baseline and smart solution implementation, as shown in figure 7. And as we can see, there is significant reduction in energy consumption due to smart solution implementation. And in addition, the results for the technical, economic, and environmental domains have been presented in tables 4 to 6. However, it's important to also mention that the ability to test and report on some of the flexibility-based KPIs, such as demand flexibility potential and demand flexibility request, is reduced, as no distribution network operator is working with the eye of white in this use case. The conclusive remark on the KPI evaluation for the eye of white. As we can see, it's evident that in the eye of white pilot sites, there has been a 93% reduction in energy consumption, which is equivalent to 643 kilowatt hour with the M7 energy storage system and heat pump, which is part of the inteGRIDy solution. And for the first use case, the building optimization, the grid efficiency and demand flexibility contributions to DSO triggered demand response services, which was based on 10% increase and 10% decrease in energy consumption, has resulted in stabilizing the grid efficiency. And like I say, this is the preliminary result for just one of the pilot sites, and we are getting more results in the course of the KPI evaluation. That's it from me. If you have any questions, I'll be happy to answer that. Thank you.
So, thanks a lot for your presentation. Let's see if there are some questions in the Q&A and in the chat. So there are some questions from the... Sorry, can you repeat? So there is a question, how do you evaluate the environmental KPIs?
Yes, the environmental KPIs has to do with the energy consumption. And from what we have here, just from what we have here for the CO2, it's assumed that the electricity was generated using fossil fuel, and as such, additional energy consumption would naturally result to an increase in CO2 emission, and that's why we've got this negative value for the CO2 emission here under the 10% increase. So the environmental, it's basically has to do with the CO2 reduction. And of course, within this very use case, it's mainly aimed at stabilizing the grid by 10% increase in energy consumption and 10% decrease in energy consumption. So, but in the other use case, which is here, you can see that due to the heat pump that was implemented within this pilot, within this use case, you can see that there has been a significant reduction in the CO2 emission for the smart solution implementation compared to the baseline solution, baseline scenario. I don't know if that answers your question.
Thanks for the reply.
Right.
Any question? No? Okay. Thanks for the good presentation. So I will ask again if there is Aggeliki Aggeli here. I think no, because we are the same people. So since there was a question probably for Bushra Cannan, I think so. I don't know. The question on the left from Ivan Rigoev. Okay, so I think it's from 1 hour ago. So I guess it is for. Sure, now it's. Oh, or probably it's even for me for my presentation. So, hi Ivan, is the question for me, Alessandro Piccinini, or for Bushra Cannan? Okay, that's fine. Okay, it was talking about the Python script. No, actually, the Python script, no, it uses the PyFMI library. So that is one of the module of the jmodelica.org tool. So basically, the script run a functional mockup unit file that is generated by using this jmodelica platform. And this, let's say that this FMU file come from a Modelica gray box model. So it doesn't use the deep learning libraries. I hope it answers. Okay, perfect. Thanks a lot. So I think that since one of the person is missing, we can close this session. So, I would like to thank all the attenders and to thank all the speakers for the great presentation. And now there is the break, so we will see you again at 11. So thanks again.
Thank you, Alessandro. See you later.
Thank you.